Hello, our honorable lecturer, Mr. Meditya. Today we're going to present our final exam, and we choose the theme of plane or flight price prediction analysis, which titled "Plane Who's Flying High in the Sky? How expensive will be flying?" Actually, these presentations will not be done if not doing together with my very interesting and really competent group member consists of myself, John Christopher Adventio, and my friends Riza and Gaga Atalafata. So, in order to make our presentation more efficient, let's head up into the materials, which will be presented by my friends.
Our final project addresses a universal pain point, blood plus volatility. We aim to build a predictive engine that doesn't just guess, but mathematically calculates the optimal time to fly. Let's start with the backbone, this analysis, the data. We didn't rely on small sample. We utilized a huge, massive datasets of 300,000 distinct flight records, scraped from Kaggle. The scope covers a 50-day window from February to March 2022, tracking flights between India's top 6 metro cities. Crucially, this dataset is rich in features. It includes not just the basic like airline and city, but complex categorical variables like flight class and derive numerical features like days left before departure. This volume and variety are what make our prediction statistically significant. Why does this matter? Because the current market is defined by information asymmetry. Passengers are currently guessing in the dark. They're facing booking uncertainty, often paying huge premiums because they don't know if a fare is fair or inflated. Our project goal is to shift this passenger from guessing to calculating. We use statistical hypothesis testing to identify key cost drivers. Is it the brand, the time, or the route? And then use the predictive modeling to forecast the exact financial impact of delaying booking, even by 24 hours. However, raw data is rarely ready for modeling. We implemented a rigorous data hygiene protocol. We verified the integrity of all 300,000 rows and confirming zero missing values. Then, we perform advanced feature encoding. For example, we map the stop variable to numeric values like 0, 1, or 2 to capture the linear progression of inconvenience. Most importantly, we applied a log transformation to the price variable. Flight prices are naturally quite skewed. New business class tickets are astronomically expensive. By normalizing this, we ensure our model weren't biased by outliers. Finally, we established a strict 80-20 trend test split to ensure our results are robust and not just result of overfitting. In slide 7 and 8, we approach a ground economic research by setting work by WCSL. We validate assemble methods like random forest consistently outperform traditional regression when handling the nonlinear complexities transportation data. We didn't just predict, we analyze behavior. Using clustering, we identify distinct business personas, like the emergency corporate referral, who book short flights last minute and price is insensitive. Our exploratory market analysis revealed a strictly divided market. Vistara and Air India operate with high variance strategy, while low-cost carriers are locked in a price war parity, where rates are virtually identical. Next, we look at the result. We run a championship between our four distinct models. Our baseline, linear regression, gives us an error rate roughly 600 and 6,767. The neural network improved this into 5,936. But undisputed winner was the random forest, which dropped the error to 5,276. Why did random forest win? Because flat price is non-linear. A single straight-line formula can capture the complex interaction between airline, class, and timing. The random forest assembled very successfully have these integrated rules.
So now let's move on into the interpretation of our chart. We have doing some coding and we also read the literature review in order to fortify our informations and our knowledge regarding our code. And now let's move into the interpretation part. So the first one is the price elasticity versus booking lead time. So as you can see, this is the graph or the outcome of our data, of our coding, and it's titled price trend as flight date approaches. So what we can get from here, the first thing is like the 15-day cliff phenomenon in the trend line reveals a distinct inflection point approximately like 15 to 20 days before their departure. So the first one is the stabilization phase, like 20 to 50 days out. The bookings made between 20 and 50 days in advance, or we had more time before or their departure, the average ticket price remains remarkably stable and flat. So, this indicates a base fare window where airline algorithms are not yet applying scarcity premiums. While the other way, the urgency search, or if we book under 15 days, or as the days left approaches zero or the more urgent, the trend line curves sharply upward. So this confirms the presence of aggressive dynamic pricing algorithms designed to capitalize on the price inelasticity of last-minute travelers, like typically business travelers who must fly regardless of the cost. So it's more inelastic the less the time left. And we also got more insight or informations regarding of this chart, which we will wait for the next slide. Yeah, so it's here, the quantifications of the procrastination penalty. So for the base average, the smoothed trend suggests an average base price of roughly 20,000 Indian rupee when booking early. But during the peak average, this rises to nearly 30,000 Indian rupee for the same day or next day bookings. So actually what we can get here, there is an approximate 50% average markup applied to tickets booked within 2 days of departure, combined compared to those who book 3 weeks in advance. So basically, the dense cluster of gray dots at the bottoms, it's representing the economy class, which forms the bulk of the volume or most of our data, and then the red trend line, the scattered dots significantly above the trend line, like ranging from 60K to 120K Indian rupee, likely represent the business class, which maintain the high price points regardless of the booking window. So the conclusion is the data validates that the price volatility is time dependent. So in order to optimize the cost, the optimal booking window is 20 plus days prior to departure, after which yield management system systematically will inflate prices in order to capture maximum revenue from urgent demand. Now let's move on into the second chart interpretations, which titled the price segmentation by time and classes. So here is the chart. The title is price distribution by departure time and class. So what we can get from here? So the class chasm is a tale of the two markets. Why we give title of the chart like that? Because the visual separation between the teal or business and the orange economy, box plots confirms that the class is the dominant determinant of the price. So for the economy class, like the so in the orange box plots, it's characterized by a high compressions. The small boxes indicate very little variations. However, the long stream of black dots or outliers suggests that surge pricing happens frequently, likely due to the last minute bookings, like we have told you earlier in the previous chart. And for the teal color or the business class, characterized by highly or high volatility. The tall boxes indicate a massive standard deviations in the pricing, and the business class ticket is not a commodity because its price fluctuates wildly depending on the specific flight. So we will wait for the next one. Okay, so the late night value opportunity, the late night category stands out as a significant anomaly in the data. So for the business class stability, unlike the other times of the day, the late night box for business class is remarkably short and sits lower on the y-axis. So this suggests that the late night flights over the cheapest and most consistent business class fares, likely due to lower corporate demand for red-eye flights. And for the economy optimizations, the economy box or the economy class for the late night is the most compact with the fewest high price outlier, making it the safest bet for budget conscious travelers to avoid hidden premiums. So the insight is the peak hour premiums. Morning and evening, the slots show the widest price spreads and the highest ceilings, reaching more than 110,000 Indian rupee. And this is aligns with the typical corporate travel behavior. Executives prefer flying out early for meetings or returning on the evening. the algorithm clearly targets these high demand windows for maximum revenue extractions. So the conclusion is the time of day pricing is highly elastic, but unequally applied. For economy passengers, the risk is in the outliers, and for business travelers, the late night window represents a strategic arbitrage opportunity to secure premium seats at the near minimum variance of prices. So let's move on to the next chart. The next chart is called the price range comparison by airline, or as we can see here, this is the chart interpretations of market positioning and competitive landscape. So this is actually a two-tiered market structure in the graph. The chart reveals a stark bifurcation in Indian aviation market, splitting clearly into the full-service carriers and low-cost carriers. The premium tier get the massive width of the yellow Vistara and the yellow and the purple here. The yellow and purple is from Vistara and Air India. The massive width of the yellow and the purple boxes indicate the extreme price variance. Vistara is the clear market leader in the terms of price ceiling, with fares stretching up to 125,000 Indian rupee. Its median price, or the vertical line inside the box, is significantly higher than all of the competitors, so it got the highest price. And Air India follows a similar pattern but with a slightly lower ceiling like 90,000 Indian rupee, suggesting it competes for the same premium traveler but undercut Vistara slightly. So basically, the market leader from the point of view of the highest price is still the Vistara and followed by Air India. So there's a disclaimer for this because this widespread is actually driven by the presence of business class inventory, which these two airlines operate extensively. So they can become the market leader in the terms of high price because they operate extensively in the business class. Now, let's move into another chart. And for this chart, actually it's titled Price versus Flight Duration. So we will interpret the operational costs versus passengers inconvenience. So the first one is the direct flight efficiency cluster, zero stops until green. The distinct markets of non-stop flights or green form a tight isolated cluster in the bottom left corner for 0 to 5 hours, and the steep upward slope of the green trend line indicates the high price sensitivity. So even a marginal increase in flight time for a direct connection correlates with a sharp rise in the price. So what we can get from this chart, direct flights are a premium product defined by speed. Passengers pay disproportionately more for every extra hour of direct connectivity. So for the next one is the one-stop mainstream market or one-stop orange. So for the volume dominance, this category represents the vast majority of the inventory, spanning from 5 to 30 plus hours. The steady upward slope of the orange trend line confirms a logical business rule, which is the longer flights equal the higher prices. This reflects the operational reality that more fuel, crew time, and airport fees generally result in higher ticket prices. And however, the massive vertical spread or the scatters shows that duration alone is not only the price setter. At the 15-hour mark, prices range from 5,000 Indian rupee to 70,000 Indian rupee, proving that the class and Ireland brand is override durations as a pricing factors. So basically, what I'm gonna tell you is the vertical spread shows that durations is not the sole determinator of the prices. Let's move on into still the same chart, but additional information. The diminishing returns of the multi-stops or two stops, or here as the purple line. So the trend line for 2 plus stops is notably flatter than the others. There is a cap on how much airlines can charge for highly inconvenient itineraries. At the 30-hour trip with 2 stops is an inferior product, and airline cannot command a premium for it. So basically, if we give not the full service, we cannot charge for premium. And the summary or the conclusion for this chart, the durations drives price, but only up to a certain point. Direct flights command a premium for speed, but however, for connecting flights, the inconvenience factor creates a price ceiling. Airlines cannot easily pass the full cost of a 30-hour multi-stop journey to the customer. So again, the duration is a determinator for the price, but not the sole determinator of the price based on our analysis. Move on into the next chart. Now we interpret the route profitability and the network strategy. So we're talking about the top 15 routes by average prices, and we will categorize it here. The Golden Corridor anomaly, or the Chennai or Bangalore. So the premium leader, as the premium leader, Chennai to Bangalore tops the chart with the highest average prices. It's surpassing the 25,000 Indian rupee. And this is geographically a very, very short distance. Approximately that's 350 kilometers or 100, like 100 mile. And the fact that it commands the highest average prices, higher than much longer cross-country flights, indicates that extreme demand elasticity happens to this graph. So basically, why we call this an anomaly? Because if we looking forward for the logics, the longer the distance, it will be more expensive, right? It will be higher average prices. But in this case, this is geographically very strange because the distance is very short, but the fact that it commands the highest price, and this is likely because a heavy corporate travel corridor where passengers pay a premium for convenience and a frequency irrespective of the short duration. So basically, the duration here is not matters the most because we can show the graph show that the short distance can also charge a premium prices due to another thing that to be considered, such as the convenience and frequency. And the next one is the cost distance correlations or the Kolkata effect. We call this Kolkata effect because look at the roads involving Kolkata or the connecting to Chiang Mai, Bangalore, and Mumbai occupy 5 of the top 10 spots. So that's why we call the Kolkata effect. Unlike the Chennai Bangalore anomaly, these are long haul domestic flights. And as you can see, for the example, it's almost more than 1,000 kilometers, and the high average price here is likely driven by higher operational baselines. So it's higher fuel consumptions and longer crew hours. These routes are expensive by necessity, not just demand. So basically this part is the counterpart of the previous anomaly. So this is one is following the logic, which means the longer the duration or the higher or the further the distance, the higher the prices. We're gonna move into the next slide. Now is the market ceiling equilibrium. There is a remarkably little variation between the top one or and the top one route 25K and the 15 positions or the last positions 22K. The bars are nearly flat in their degradation. So this is suggests a price ceiling in the domestic metro market. Regardless of the route's popularity or distance, the market struggles to sustain an average price significantly above 25,000 Indian rupee. Competition prevents any single route for becoming a massive outlier. So basically, we want to connect this into logic, and it's actually logical because if we got a lot of competitions, we cannot determine a single price of our own. Sure, we can determine the price of the flights. For example, I will charge like 500k Indian rupees, but nobody will buy it. So yeah, basically the competition will prevent any single route for becoming a massive outlier. So the summary is route pricing follows two distinct logics. The first one is operational costs, as seen in the long haul Kolkata flights, and the corporate demand, as seen in the short haul Chennai Bangalore premium. So in the charts, we got two basic group. The first one is the logical path, which we call the operational cost. The longer or the further the destinations, it will be more costly. But there are also some anomaly which also uh, shocked us before, which is the short haul Chennai Bangalore premium. They have a very very short distance, but they got a premium because of the convenience in their experience of flight. So moving on into the next slide, we are gonna analyze more about the chart, and it's probably the last chart I will analyze by me, and it will be continued with my other friends. So the last thing is the operational complexity versus the pricing power. As you can see here, it's called the price distributions by the numbers of stops. So now we're calling about the number of stops. There is a terminology called direct flight or one stop, yeah, just direct flight. So we're going from from our places to our destinations. It's a direct flight. So surprisingly, the direct flights show the lowest median price and the most compressed interquartile range. Like here, the small pink box. So this segment is dominated by short-haul LCC or low-cost carrier routes, where efficiency can keep the base fare so low, while outliers exist up to 60K Indian rupee, but this is the most predictable pricing tier for the consumer. And the next one is the one-stop volatility engine, or one-stop blue here, the box. The number of stops increase to one, the number of stops, or the one stop, and the previous one is direct flight, so there is no transit, and the number of stops increasing to one, or the blue box plot. That means we're gonna make a one stop or the transit, yeah, we will call it in Indonesia. So the maximum variance say that this is a massive spherical spread of the blue box spanning 5K to 50K Indian rupee indicates extreme volatility. So this category contains the wildest mix of inventory from cheap connecting flights to premium long haul business routes. So basically in the category or in the cluster of one transit or one stop, we get a lot of variation in the data as we show in the graph, and the outcome says so because we can see there's a wide mix of inventory from the cheap connecting flights to the premium long haul business routes. So basically our data is really spread it here, is really massive in this category, which is the transit or the number of stops, one or the one stop, and it is the primary playground for airline pricing algorithms, resulting in the highest price ceiling reaching 125,000 Indian rupee.
All right, uh, we're going to the hidden driver of cost. The As you can see, this is the correlation matrix of the numeric variables, and there's a distinct negative correlation between the price per hour and both durations and stop, and the correlation between days left and price is surprisingly weak. Like the relationship is not linear. You can see on this. Okay, the next one is the hierarchy of pricing power. Like this is the feature importance. We use random first, means the higher end MSCs is more important. The number one is class, second one is days left, the third one is source city, and the fourth is airlines. Alright, we're moving to the predictive reliability analysis. This is the actual versus predicted price. We use random forest with accuracy of 94%. It's pretty high among other models that we have tested. The other model have very high RMSEs, and this model have pretty low RMSEs, around like 5,200. And the that means it's capture basically all of the versions what airlines charge. The predictions are tight, and the average error is about 50,000 rupees. Like economy bookings, nearly perfect. Like still very good lah. Just okay, and the class is the main driver. Managing set inventory by class. That's what the drives around revenues, not tweaking routes of departure time. Okay. So the next one is the key business insight. I said that the class is the main price driver, and the next one is the timing matters more than the brand, because days left is the second most important predictor, outperforming airline and other road as price drivers. As a light minute economy tracks, as a low cost carrier can be more expensive than a early bird ticket on the premium airline. And the second one is this the 20-day sweet spot. The ticket price remain specifically relatively flat around like to 20,000 rupees when booking like 20 till 50 days before departure. And the next one is the profitability customer personas. Like source flights book very close to departure with a low price sensitivity leads to ideal targets for aggressive dynamic pricing. The next one is the market and network. The two-tier airline landscape, like Vista and Air India, from the premium tier with very wide price lines and ceilings, capturing a high-yield business travelers. And route profitably anomalies like the Chennai Bangalore road is short in distance but the highest in average fare, making it the most profitable corridors in the terms of revenues per mile. Okay, this is the last one. This is the strategic recommendations for the airlines. Street class and days life as the main levers in the pricing strategies, with airline and roads as secondary environment. And we use because we use the three base models as they can also use it to automatic economic pricing when the model achieve high accuracy like our model, and design explicit pricing rules for bookings under 20 days to automatically monetize urgency. And for the customers, book at least 20 days in advance and avoid last minute absolutely, and use time of day to your advantage. Okay, we're moving to the final conclusions. This analysis is revealed that the airline pricing operates according to the strict hierarchical logic, not a random fluctuations, but a systematic rules that passengers and airlines alike can understand and optimize.